Hello. I'm excited to be here at the DNAC Health Networks meeting for 2022. I wish we were doing this in person, but such is life, I guess. I'm Alex Volfovsky. I'm an assistant professor in the statistical science department at Duke. And I'll be talking a little bit today about different network models and where you can leverage some community structure, either to improve the way that you do link prediction or improve the way in which you run experiments. So why do we model networks? And I recognize that this is a group that probably does not need this type of introduction, and you've watched all the other videos as well. But in general, our goal is to understand the formation of relationships and maybe try to intervene on them. And there are sort of applied fields across the gamut that are interested in different networks. So you might be interested in how friends form, you might be interested in how information flows across contact networks, you might be interested in how disease is transmitted over a particular network of contacts. And while we won't spend time on the sort of statistical theory questions that arise when you try to model networks, I do want you to keep them in mind, sort of in the back of your head as you're listening to my presentation. So at a high level, we're going to need to make some assumptions about what a network is and how different information about the individuals in the network leads to them forming their relationships. And of course, when you make assumptions, they might fail. And so you might be interested in settings where those assumptions do fail. So say you assume that there's some kind of community structure, but there really isn't. What happens then? And sort of at a high level, our goal is to develop fail-safes to overcome these problems. We won't have sort of an in-depth discussion of these fail-safes, but at again, a high level, what I'll propose, the models I'll propose in this presentation and sort of implement have the ability to sort of revert back to simpler models. And that's going to be sort of the fail-safe of what happens if some kind of assumption fails. And the two application areas that I'll be thinking about, one is going to be causal inference. How do you run better experiments? And another one is going to be in link prediction, or maybe not necessarily just new link prediction, but also explaining why certain links exist. So you might be, this is sort of close to questions in sociology about why friendships form and so on. I will sort of form this within the context of regression. So here's an economic model. Imagine that you have information about exports from country to country. So Yij is how much did country I export to country J, and maybe you're going to look at differences from year to year. So Yij is the difference between year 1 and year 2 for a particular country pair. And you're interested in relating that to some predictors. So say you have information, these Xijs maybe are log GDP of the different countries. And you think that log GDP has some kind of influence on exports from year to year. And imagine that you know nothing else about networks and you run this regression, completely ignoring any kind of potential structure in the data, and you end up with these residuals. So these are residuals of particular eigenvectors of the residuals, but as you can see, there's a lot of structure here, right? You have the European countries sort of at the top. If you look at the left plot, you have Asian countries on the bottom. And the one thing to sort of take away from this plot is, as you might remember from sort of interest sets, if you have structure in your residuals, that means you didn't do a great job really accounting for all of the variability in the problem. And so you need to go back to the drawing board. And so maybe this assumption of independence in the errors is inappropriate. And that's going to be our sort of first point of departure when we're designing a network regression model. So sort of the first order thing that people might do is assume complete independence and do something kind of ordinary least squares. Let's imagine that you know what the dependent structure is in the epsilons, then you might do some kind of GLS or generalized least squares where you adjust for that covariance structure. It will turn out that for us, it's easier to sort of conceptualize what this additional dependence looks like in terms of multiple different terms. And so we won't necessarily be fitting generalized least squares models, but this is going to be the general level of approach. On the causal inference front, imagine that you're Facebook and you're interested in changing the algorithm for everybody, and you're interested, hey, is that going to make me more money or less money? And obviously you can't just go ahead and apply this to everybody in your network, because if it was the wrong change, then you might lose a ton of money. And so you need to estimate this total network effect by maybe running a small experiment. So we're going to think about this as the global average treatment effect. So this is the treatment effect of treating everybody. And imagine that YI is amount of money spent by a particular user. And you're interested in what happens if you treated everybody versus treated nobody. And what's really nice is that there's an experimental design that really gets you access to this particular quantity of interest called graph cluster randomization. And it sort of uses this idea that you can potentially reduce the space of interesting randomizations on this network by thinking about who of your friends or who else in this network might actually affect your treatment, your response to treatment. And so what they do in this graph cluster randomization technique is they cluster the graphs, a graph in a particular way, and then they assign a whole cluster to a particular treatment. In order to sort of think about, you can think about each of these clusters as a microcosm of the whole network. We're going to come back to this and we're going to try to inject a little bit more structure, maybe based on observable or even unobservable information, in order to improve this experimental design even more by thinking about what kind of networks we're dealing with. So at a high level, our goal is to do better network regression. I'm going to start with sort of the fundamentals of network regression that's implemented in the AMEN package in R. Then we're going to try to think about this latent network community structure that might exist in order to improve our regression. The code for that is available in this GitHub repo, and I'll talk a little bit more about how to run that. And then the last thing I'll just mention is what to do with leveraging latent network structure to improve experimentation. And what's great here is that you can actually use pretty much any off-the-shelf community detection tools in order to do better than just the basic graph cluster randomization. All right, so here's our setup. We're going to have n individuals or n nodes or n actors, and I'll try to stick to one of those words, but I might use them interchangeably. And we have some kind of sociomatrix Y, where the entries of Y quantify the dyadic relationship between two individuals. So Yij is the relationship between I and J. And it could be that it is symmetric, so Yij is equal to Yji. In this case, this could be sort of reciprocal friendships. Or it could be directed, right? Number of emails that person I sent to person J. In the same theme, it's very likely that the diagonal is not actually well defined. In the first example we saw with country exports, obviously one cannot export to themselves. Friendships to themselves are not very well, to oneself is not very well defined, and so on. We're not going to worry about the fact that it's undefined because It's not actually going to affect our inference. It might make computation harder, but it doesn't affect anything on the surface. And we're going to have two types of covariates that we might be interested in relating their behavior, the behavior of individuals as sort of node-specific people to how they make friendships, or dyadic relationships. So node-specific information could be the person's age or the person's income, and a dyadic specific covariate could be, do they belong to the same club? So you want to be able to sort of differentiate between these two objects. Our first order model that is going to help us deal with some of this excess dependence that was not captured when you just assumed that all of the errors are independent, thinks about the network in terms of senders and receivers. And you can give an actual interpretation to these parameters. So sender effects are about sociability. If I have a big sender effect, then I am a very social person. I want to make lots and lots of friends. And receiver effects, which is popularity. If my receiver effect is very big, it means that lots of people want to connect to me, no matter how sociable they are. This was introduced as the social relations model, which can really be thought of as an ANOVA type of decomposition of a matrix. I write it as almost an ANOVA because in reality, these sender and receiver effects really tell us some information about the same individuals, right? So AI is the sender effect of individual I, it's their sociability, and BI is the popularity of individual I. And so from an actual model development perspective, you might want to relate AI and BI in a way that you normally wouldn't in an ANOVA. So what's great is that you can write down this general model, the social relations model, which decomposes any kind of relational matrix, this n by n y matrix, into a sender effect, a receiver effect, and maybe some kind of overall mean. And then we could say, okay, well, I want my sender effect and my sender and receiver effects for popularity and sociability to be correlated for a person. So a very popular person is probably also very sociable, and a very sociable person is probably very popular. And so you want to be able to build that in. Furthermore, you might want to build in some kind of reciprocity. So if we're dealing with directed connections, if I say that I'm your friend, it's very likely or more likely that you will say that I am your friend. And so this type of dyadic correlation can be introduced by adding a correlation in these epsilon ij terms that's captured over here. This already puts substantial structure on the potential dependence within a network regression. And it can really help in capturing sort of excess variability, and in turn help with estimating coefficients. Note that there's no covariates here, but this sort of is a broad spectrum description of the network. Once you want to introduce covariates, you do this in a way that's sort of very similar to any other type of regression problem, except that now instead of just having an X transpose beta type of term, you might think about separate types of covariates. So you have dyadic covariates. This is information about the pair of individuals, whether or not they belong to the same community, or whether or not they both like to do something. Those might be more important or equally important to just knowing whether or not somebody having a particular level of education leads to them having sending out more connections or receiving more connections. It's actually very common, at least in practice, if you look through the literature, to implement this type of model, to run this type of model by thinking about the row and column covariates being the same thing, really. But that's not absolutely necessary, and the code that we've built out for this does not require that. So a particular example of where this is not necessarily true, right? Popularity might be affected by athletic success. So maybe somebody winning a bunch of athletic awards could be a receiver effect, but probably doesn't have much effect on their sociability. I'm including the code to run these models down here. I'm going to come back to thinking about this code at the end of the talk. And again, I'm happy to field questions about it at the end as well. But unfortunately, while this model feels like it's sort of complete, it's actually missing something. And what it's missing is the ability to capture higher order effects. While it's able to sort of capture the randomness in popularity, or the variability in popularity, variability in sociability, these are still additive. But it turns out that a lot of real human behavior is not just additive. We want to be able to say something about how similar individuals are likely to connect to each other. So that can be, we can start capturing that with those expressed dyadic effects, but there could be additional latent homophily of that sort. Similarly, there's the notion of stochastic equivalence that is observed in real interactions, where similar individuals tend to act similarly. And that really can't be captured by any of the terms that are currently in that model. But you really do want that if person I connects to person K and person J connects to person K, that you want to be able to predict those two things in case, if you know that I and J are similar individuals. So here we have a plot from a paper by Peter Hopf from 2008. And you see on the left here, sort of an example of homophily where my friends are likely to be friends with each other. And on the right, we see an example of stochastic equivalence where you see sort of three communities where there are essentially almost no ties within communities, but lots of cross-community ties. And so people in each community do behave similarly, right? But don't necessarily connect to each other. It's very clear that the aforementioned models are unable to capture both of these behaviors simultaneously, even though we might be able to start capturing things about homophily. Because essentially we can't go beyond second order dependencies. You can think about homophily as being captured in terms of these dyadic covariates that are constructed from individual level covariates, right? So if you think about xi and xj as saying that person I belongs to a particular club, and so xi xj is the indicator that both people belong to that club. And so if there is in fact some kind of homophilous interaction due to belonging to that club, that type of covariate would capture it. In fact, you can construct sort of lots of generalized versions of these, but while that can be baked into the AMN framework, there's still additional excess covariance that you might want to account for. And this suggests introducing latent or sort of random multiplicative effects. So this sort of draws a parallel to a sort of observed homophily that can be placed into the dyadic covariates, and now introduces it as a multiplicative random effect. Let's think a little bit about why these multiplicative effects are going to allow us to capture triadic or sort of information that is beyond second order. You can think about that as sort of trying to capture something about transitivity. So UI is going to be our information about the sender. VJ is going to be information about the receiver. And so it's clear that if UI is approximately equal to VJ, it doesn't matter if UI is negative or positive, because we can think about them living in sort of a large high dimensional space. But if they're about the same, then you know that UI transpose VJ, this inner product, is going to be positive, which is going to necessarily increase the frequency of interactions or the measurement of the interaction between I and J. Similarly, if you know that UI is approximately the same as UJ, right, then their interaction, person I and person J's interaction with person K will be similar because UI transpose VK and UJ transpose VK will be similar. And so that's going to allow us to capture stochastic equivalence as well. So similar individuals are being captured by this multiplicative effect, and also stochastically equivalent individuals are going to be captured by this multiplicative effect. And as a special submodel, you can think about stochastic block models as living in this class. And in fact, we're going to leverage that idea in a second to sort of expand this model to allow for essentially similar behavior to these multiplicative effects to pervade our predictors as well. So as a quick aside, we're not going to delve into sort of the mechanics of how to fit these models for binary data. But in general, we observe binary interactions, right, or counts of interactions. And so you could think about Yij as being 1 if I is friends with J. What we would usually do in order to actually fit these models is to think about an embedding of this binary variable Yij into a latent space. So for example, Yij is equal to the indicator now that Zij is positive. And then you would model Zij as being this, as coming from this universe. So this is exactly the model that we had before, right? And so it will allow us to interpret parameters in a very similar way as before. And it allows us this function, this indicator that Zij is greater than 0, ties together the observed value, right, with the information about the covariates. It's possible to sort of expand this to count data. So this, instead of being an indicator that Zij is greater than 0, this could be some other function that will map the observed values to this latent thing. But the machinery will remain the same. And what's nice is that the interpretability of these parameters remains the same. So no matter whether or not you're thinking about them on the observed scale or on the latent scale. So let's take a look at some data. So I am hiding a little bit about the details of how this data, this model is fit, but it's all available in the paper. The general idea here is that we take a Bayesian approach and we place priors on the betas. We place we have a model, right, for A and B, which I introduced before. We have now a model for the U's and the V's. We have some correlation for the epsilon, so we put a prior on that correlation. And then we can actually derive a very nice Gibbs sampler for most of these parameters. And then we need one more metropolis step for the correlation. So this is very amenable to Bayesian analysis. And as we'll see, this seems to perform very well. So what kind of data are we going to talk about? I'm going to give an example from AddHealth, where we're interested in relating these network characteristics to individual level behavior. And that might be because we're interested in identifying at-risk youth or developing some kind of interventional programs, either directly on their health or designing peer interventions, sort of identifying communities of individuals that might be able to positively influence each other. And there's a large literature on these network models. I'm concentrating on these latent variable models. And I just want to point out that the current state of the art makes two assumptions. First, that the data are fully observed. And second, that the effects of covariates are sort of the same across all units, across all individuals. We're not going to have time to talk about this data are fully observed assumption, but that is one of the assumptions that we addressed in earlier work, where it turns out that in actually all three of these listed data sets, we actually don't fully observe the data, the network. We only observe a partial network. And so you have to somehow account for the fact that individuals could not nominate more than 5 or more than 10 friends. What we'll concentrate on is identifying how we can inject some kind of differentiation between the effect of covariates on different individuals. So we're going to take a look at the male-male friendship network from one school in AddHealth. AddHealth is this huge nationwide study of American adolescents. They went into a lot of high schools and middle schools and asked them to describe who their top 5 male and top 5 female friends are. And then they collected a ton of information about the individuals involved in the study. It's easier to think about just modeling same-sex networks here. So we're going to just look at the male-male friendship network from a single school. And we picked some covariates, some predictors that might be informative of why ties come together, why what might make somebody more popular or more sociable. I'm only showing you the row and column effects here, but there are also dyadic effects about being in the same club or being on the same sports team. What we can see here is that there's a column effect of sports involvement, it seems, maybe. These are credible intervals rather than confidence intervals. There seems to be something going on with the race indicator here that might be negatively correlated with having friendships. But in general, it looks like there's not a lot of information in these covariates to predict whether or not individuals will be friends. Now, if that were truly the case, you could go out and say, well, I guess if I, observe that there's a lot of smoking in this school and it doesn't really predict friendship, then I kind of need to develop an anti-smoking intervention that sort of equally disperses across the whole school. But all of these zeros to us felt a little bit suspect. And so what we did is we applied a community detection algorithm and then ran the AMAN models. And what you're seeing here is the results for the same school, but we've now run the model twice, once on the graph that's induced, or the subnetwork that's induced by community 1, and once on the subgraph that's induced by community 2. And as you can see, while the results are, in the same theme on overall, and we're going to actually show analytically that they have to be on average, we see that in community 2, there seems to be a positive effect of GPA on the column effect. It looks like smoking has a negative effect here for community 2. Similarly, sport involvement might be a little bit low, and so on. So we're seeing some kind of difference between two latent communities, right? I'm not telling you how we constructed them yet. In this case, we just ran a fairly naive algorithm. But maybe if we can simultaneously learn the communities and study how how covariates predict friendship formation, we would be able to do better. So this is joint work with Heather Mathew, who actually just defended and just graduated, in fact. And what we don't have access to in the original AME model is to community structure that affects anything other than the multiplicative effects. So the multiplicative effects, remember, are this UI transpose VJ or UI transpose UI. And if you think about how you might construct a stochastic block model, so stochastic block model is a model that says that individuals belong to one of a few communities, and the probability of an interaction between two individuals, or a probability of a tie or a friendship, only depends on their community membership. So we want to enhance our model to allow the coefficients for each individual, for each covariate, to potentially depend on the group membership or community membership of individuals, of the person. So let's look at the row predictors, right? We no longer do we just have a beta transpose R X Ri. We're interested in this beta being a function of maybe some kind of community structure. And what we're going to need to do is tie together this function G with something about our multiplicative effects. Because again, the multiplicative effects can play the role of describing being in the same community or being in different communities. So if we do that, we need to relate this, right? And we'll first abuse notation a little bit and change this UV transpose to UDV transpose. We'll do that just because we're going to think about the U's as being binary matrices. And so we might want a little bit more variability, which will allow us to introduce this diagonal matrix, or maybe not even a diagonal. Now we'll think about the U's as being a matrix, an n by k matrix, where exactly one entry in each row is a 1. So the rows are representing the community membership of each individual. And so if a particular column is equal to 1, that means that that person belongs to that community. Similarly, you could think about having different communities for each individual as a receiver of ties. In practice, you probably usually will think of U and V being the same, but this gives you a sort of additional flexibility. So we're going to try to link these beta tilde R and beta tilde C, which if you think about what they are, if there's 3 possible communities, then beta tilde R for covariate, for one of the row covariates would be beta tilde R, beta R1, beta R2, and beta R3, right? And so we need to be able to write down this equation without this inconvenient G notation, and ideally in terms of these U and V. So we're going to do it in the following way. So U is going to be an n by k matrix. K is going to be 3. There's 3 communities, and there's 4 individuals. And here again, our goal is to try to figure out notation that will extract beta tilde R1 for individual 1 if they belong to group 1. So here we have our U matrix over here, right? So person 1 is in community 3, person 2 is in community 2, and so on, right? And our goal is to extract the right information. Sorry, person 1 is in community 1, person 2 is in community 2, and so on, right? This is U transpose. So turns out if you look at this and write it down as a diagonal matrix, and then multiply this by a repeat of the x's, you're actually going to extract exactly the information that you need for this equation. So that's extremely promising that we're able to write it down in terms of simple linear algebra operations. So it turns out that you can actually write down this equation. Here we're only looking at row and column covariates, but there's an equivalent representation for dyadic covariates that depend on the different community structures. And we're able to actually think about how you would go ahead about actually learning these new parameters, these new beta tildes. The first question that you might want to ask, though, is how does this actually relate to the standard additive and multiplicative effects network model? And it turns out that it's a simple version of this actually says that these beta tildes on average are the same as what you would estimate if you did not have this additional structure. So what this is saying is if you're using the Amen model and there is community structure, but you ignore it, you're actually estimating an average, which is sort of what we saw in that first example with the data. So here's a simulation. I just want you to see sort of that this idea works and that the code that we introduce works for this. Again, we're take a very Bayesian approach to this. We put priors on everything. This complicated the actual fitting a lot, and we can delve into sort of the code that is there. Essentially, updating the U's now became more complicated, and we had to come up with a few clever ideas of how to do that. This is sort of a nice generalization of the AMEN model. So let's imagine you have 150 people. There's 3 communities with 50 individuals in each community. This is the structure, right? So there is a dyadic coefficient. There are row covariates and column covariates, and there's 2 of each of them. We're now going to assume that the first row and the first column covariate are actually community independent. So you could just write it in the old format if you wanted to. Well, the second row and second column covariates are community dependent. And so most importantly, they have both positive and negative values, and on average, they zero out. And so what we're going to do is we're not going to know about it, and we're just going to fit the regular AMEN model and the one that doesn't know anything about which covariates are community driven, which community covariates are not community driven. What you see on the left is the AMEN model. For the community independent covariates, it does really well. It has nothing, it doesn't need any additional information because it just learns those parameters. On the other hand, for the dependent covariates, it's not doing well at all, right? The community dependent ones, it's actually estimating the average, as I suggested that it would. On the other hand, the community dependent model is able to distinguish the different community variables. I want to note that actually there's a lot of potential non-identifiability here because of the way that the model is structured. So what we're plotting here is actually not posterior credible intervals, but a post-processing of posterior credible intervals that we can go into later on. But importantly, you also see that for the community independent covariate, it estimates the same value for all 3 communities. And so maybe some future work is doing this adaptation explicitly and actually collapsing this into a single value so as to not waste energy on trying to update 3 values at a time. So we've applied this to 2 different schools. The first is School A, I believe, is the one that we saw pictures of. So we were able to find 2 communities here. These communities are being found simultaneously as we're fitting the actual regression. We see that the communities are not just splitting across a specific predictor. So it's not like everybody in community 1 is a smoker and nobody in community 2 is a smoker. These seem to be fairly mixed communities in both settings. And so this does suggest that we're identifying some kind of latent behavior in these communities rather than just capturing some kind of predictor. But we'll see that in School A, there's some differentiation between the community structure, between the different covariates, whereas in School B, there's substantially less differentiation between the communities. And so it doesn't really matter which, sort of, what's nice here is that we're able to fit this very general model and not be worried that we'll end up with sort of somehow fitting an incorrect structure. So we're able to adapt down to settings where there is no community dependence. But here we see that, it looks like smoking might have differential effects, even though the credible intervals are a little wide here. It does look like smoking might be playing different roles in the different communities in School A. So now that we have this model that allows us to evaluate some data, so we've seen that community structure is actually very, very important. And so I want to take a slight detour to come back to the graph cluster randomization that we started with to talk about using community structure in order to improve experimentation. This is a short detour, and we'll conclude with sort of just looking at the code base for the AMEN models and the community-driven AMEN models. So recall, right, to your Facebook, you want to change your ad algorithm, and you can't do it to the whole graph, so you have to figure out a way to estimate the total network effect without doing that. And graph cluster randomization suggests that you take a network, you cluster it into small universes, and then you randomize each of those small universes into treatment or control. And then you can compare outcomes from treatment between the treated and control individuals. What you're seeing on the bottom here is a particular network. In this network, triangles are one community and circles are another community. And the colors represent the clusters that graph cluster randomization creates. And so they would treat the red cluster maybe and not treat the purple cluster and treat the blue cluster. And so, or some other combination of treat, don't treat. What's important to note is that while red and blue are completely within community clusters, purple appears to be a cross-community cluster involving both triangles and circles. This might be perfectly reasonable for a particular study, but we're going to make the argument that that's not necessarily the best. One of the issues when trying to learn about these type of quantities where everybody's treated and not everybody's treated is the concern that your friends might affect something about your outcome. And so one of the common assumptions is that only my friend's treatment affects my outcome. And so in that case, this is a perfectly reasonable way to think about it. You completely don't care about the community structure. But what if community structure is somehow informative? So there's definitely a large literature on differential behavior within and between communities. And so this suggests this novel assumption on interference, which we call community interference assumption, that says that only the treatment of my within community friends can affect me. In turn, this suggests that we need a new design because we really don't like this purple one, right? So how do you do this? Well, so the old design looks like this. The new design looks like this. This community-aware design, all it's doing is you first do community detection using your favorite community detection algorithm. And then conditional on the community detection, you apply graph cluster randomization within each of the communities. This only really makes sense when you have very large communities that you think are going to be relevant, and then you want to apply graph cluster randomization in order to find close-knit clusters, which might not be the case when you apply different community detection algorithms. So the main difference, even though the two graphs are the same, the main difference is that in the bottom graph, everybody in the same color has to belong to the same community. And so we ran some simulations. So we generated data according to our community-informed, that sort of fit within the community-informed universe. And what you're seeing here is relative bias plots. So the worst bias is going to be due to just coin tosses. So what's called Bernoulli randomization. And so numbers below 1 are good, right? You want to have a smaller relative bias. In red, you, and this is mainly numerical differences, in red, you have the standard graph cluster randomization approach. In black, you have the Oracle community graph cluster, community-driven graph cluster randomization. So these don't really change over the x-axis because the x-axis does not affect them at all. What the x-axis is capturing is how hard is the community detection problem. So you have probably seen that there's lots of different community detection algorithms, and some of them perform well in certain settings, some of them don't perform well in other settings. For a particular community detection algorithm here, which is just spectral embeddings, we are able to compute the misclustering rate, so how good this algorithm is. And we see that as it becomes harder and harder to correctly identify the communities, our adaptive approach, our community-driven design, performs worse and worse, tending towards the original graph cluster randomization. But it does not perform substantially, does not perform as poorly as that, even when the community detection problem is hard. But that's kind of nice, right? So even if we are doing fairly poorly on community detection, which is very common, we should still be able to recover some kind of higher quality estimate than just randomization, sort of Bernoulli randomization, or even the original graph cluster randomization. I don't have the plots in here, but in fact, we can break the assumption and so have the true model be sort of the standard one based on the standard assumption that all of my friends' connections can affect my, all of my friends' treatment can affect my outcomes. And there, what's nice is that our community-driven approach performs approximately the same as graph cluster randomization. So even while our assumption fails, we don't actually lose that much in actual performance. So if you remember the theory questions that I asked at the beginning, this is one of those settings where we're fairly confident that our proposal is very, very adaptive and is able to not lose too much, even when it's incorrect. This sort of is all of the main topics that I wanted to talk about. What I have below is just a few slides that describe the code necessary for running the network regression problem. Probably the most full-fledged code that is available as a package on Crayon is the AMEN package. It has this one function, AME, that takes in all of your data and is able to perform this MCMC on pretty much any computer fairly quickly. I mainly just want to point out the Y here is a square matrix of some kind of relation. So it's either a binary matrix or a non-binary matrix. You can have it have missing values or not have missing values. This is perfectly fine for all of the code here. Then you are asked for three types of covariates, right? So predictors of either row predictors, column predictors, or dyadic predictors. So popularity, sociability, or dyadic information. RVAR and CVAR tell you whether or not you want to fit row random effects and column random effects. If you remember, this is our social relations model parameters. DCOR is whether or not you want dyadic or reciprocity correlation. And NVAR is if you want to introduce nodal random effects if you're dealing with symmetric data. The last thing that you need to specify if you want to sort of go to our most flexible model is the dimension of the multiplicative effects. This is a hard problem, and in fact, this is something that we can spend a lot of time discussing. It's not obvious what the right answer is, and so one thing you could do is you could choose lots of different R's, fit the data, and ask, are my data being fit well by this model? We're not going to sort of delve into the different types of models that are available, but there's one that's sort of continuous data, binary, ordinal, and then you have censored binary fixed rank nomination, which is the model that we introduced to deal with the fact that data like AddHealth are not fully observed. And then this is another rank likelihood. And OD max is a parameter necessary for these not fully observed data. So the main takeaway here is if you download this, if you install this package and you have some dyadic data and you have some predictors and you want to introduce some kind of latent effects, either additive or multiplicative, this will allow you to do that. As you run this, I'm going to skip the details here, but we can get back to them if it's of interest. As you run this, it's going to produce this goodness of fit statistics for the Markov chain. So what you will see at the top is some information about, this is a trace plot for the Markov chain, so you can assess some kind of mixing. And then you have 4 different posterior predictive checks. Posterior predictive checks are very convenient tools that allow you to ask the question, are the data that would be generated by the current model parameters, do they look anything like the data I actually observed? And so here you see that it seems like 3 of these posterior predictive checks are approximately good, right? So the red line is the observed data, and then these the blue histograms are the posterior predictive distributions. And then one of them seems to be very, very bad. So if we look sort of deeper into what these are, you can compute standard deviations of row means, standard deviation of column means. These are sort of fairly obvious quantities that capture whether or not simulated data have the same amount of information in each row and in each column. Dyadic dependence is just a measure of the correlation. And again, are the data that you're generating capturing any potential dyadic correlation? So these are, I would say, sort of first, second order type of quantities. Triadic dependence is attempting to measure something about transitivity. Is transitivity being captured? And in this specific instance, I believe that the model actually doesn't include the multiplicative effects. And so, but the simulated data actually did have multiplicative effects. And so you see that the model is unable to capture it. The data that the model is, that when you're doing the model fit, the posterior predictive distribution seems to be centered around 0 here, or negative, but the true value is 0.2 for the triadic dependence in the data. So this would suggest that you should go back and maybe crank up R to allow for more information to be captured. To fit the community adaptive network regression, it's almost the same code. It's actually based on the same code base, but because it required some tweaks, this is still only available on GitHub, and we're sort of working to slowly integrate this into the same ecosystem as the AMEN model. So if you go to this website, you're going to be able to download all of the code that's necessary there. There's some package dependencies you'll need to install. What's important is that mainly everything in this function is essentially the same thing as in the AME function in the package. So you need to feed it some observed network. In this case, we're dealing with binary and censored binary ones, but this is easily adjusted for continuous data as well. And then you need to give it row covariates, column covariates, and dyadic covariates in the same format as before, sorry, in a slightly different format than before, but we have functions to pre-process it. So essentially you want to do repeated versions of the row and column covariates because it's going to ease calculations later. The number of iterations for the MCMC to run is in here as well. And this number of groups, it's the number of communities that we have, and this can be thought of as choosing an R in the original AME function. We've added a little bit more flexibility here to allow you to change the priors for the different parameters, though most likely keeping the defaults is just as good. And then here we have sort of asking whether or not you want both a U and a V. So you want the communities that people belong to as senders to be different than the ones that they are as receivers or not. These are sort of just parallel to the functions in the AMEN package. The last few things that we want is we can specify whether or not we're interested in learning all possible covariates to be dependent on the community structure or not all of them. If you don't select all and instead choose some, then you need to specify which ones need to be independent. So one is obviously the overall mean. So these are new things to push through. This is just some information about what you want to keep track of and how much burn-in to do. And then the last part, while we didn't talk about it, it turns out that there are good and bad initializations for the Markov chain here. And so if you keep this at default, it's going to initialize to a good place. And you should be able to change the prior for the group probabilities as well. So thank you so much. The papers are in archive. There's code on GitHub. This was graciously supported by NSF Career, ARI, and the National Institutes of Health. All of the work here was that I presented was joined with Heather Mathews, who just graduated. And so all the credit should really go to her. You can access all of this on my website or on the links that are provided throughout the presentation. So thank you so much.